The broadcast is now starting. All attendees are in listen-only mode.
Hello, welcome everybody to Coffee with Caleffi. We've had a great topic today. Jody's going to be the presenter, talk about multiple temperature and systems and hydronic systems. He's the perfect guy for this job, so he's had a lot of experience in boiler work, so I think you're going to enjoy this, spend a lot of time on it. So, hydronics, 18 will probably be out February on water quality. This is what we've got so far. These are also available as a PDF if you want to look at some of the past issues there. Make sure you're on the list to receive these in the mail. This is an excellent product that we offer for free to help you guys. Take it away, Jody. Thanks.
Thank you. So today is going to be hopefully an action-packed hour. It's really about water temperatures. So we're going to talk about the first water temperature. And for me, that's really about what's going on in the hydraulic separator. You know, many times in my past, I've talked to guys, and the question has come up, you know, as far as, you know, you told me that we're going to run on this heating curve, but in the end, I ended up running hotter, and there was a question about why that happened. We'll talk about how many different water temperatures do I need, and then we'll go through the various methods of delivering a lower water temperature, a second or a third or even a fourth water temperature in the system, and then we'll finish up talking about indirect water heaters. Now, question always comes up when somebody's looking at a design or looking at a building and saying, well, how many water temperatures do I need? Why do I need multiple water temperatures? A lot of reasons that this happens. You know, one that happens quite often is an older building gets a new addition. The old building was built in the mid-'80s. The new addition is going in with radiant or some other technology requiring a different water temperature. Now I'm into a second or maybe a third water temperature. Does different parts of my building have different heating requirements? Maybe a higher or lower heat loss requiring a higher or lower amount of heat coming in there. You know, a basement, a below-grade basement is going to have a much different heat requirement than a room that has a wall of glass. So a lot of times the heat requirement drives the different water temperatures. Sometimes it's driven by recovery. You know, certain parts of the building are not utilized on a regular basis, and I may have the need to quickly bring rooms or parts of the building up to temperature much quicker than other parts of the building. So I may require a different water temperature to make that happen. Could be different heat emitter technologies. We see a lot of mixed heat emitters throughout the building driving different water temperatures. This one happens often, different heat requirements in the building. The one that always seems to come up is the in-law apartment. You know, I need the ability to drive a higher temperature in the in-law apartment than the rest of the building. You know, if I can, let's run on 2 water temperatures to improve the efficiency of the system. But there's always the need for these different water temperatures. Let's talk a little bit about heat emitters. You know, how many temperatures do I need? Do they need to run off of outdoor reset? Because the reality is a lot of systems are mixed where some of the temperatures are fixed and some of them are going to be outdoor reset. You know, radiant, we can go an above floor radiant system, a below floor radiant system, or a slab-based system. Probably every single one of these require a different water temperature. And based on the flooring or the floor covering, I may have the same type of radiant system throughout the building, yet because of the floor covering, I need multiple water temperatures throughout that building. Now let's throw in a little hydro air. Happens all the time. That now becomes another water temperature. Some of the building may have panel radiators. Some of the building may have baseboard. All of these requiring possibly different water temperatures or different combinations. And then, of course, you know, the standard for a lot of systems out there is an indirect water heater. I add that in there, all of a sudden I have something that I don't want to run off of outdoor reset. I'm going to run it off of a set point, and it's probably going to be at a higher set point than any other load in the building. So when we start to look at designing systems, the need for multiple water temperatures come up quite regularly. I want to look at a couple of systems that came in with our Caleffi Excellence program. So here's one from one of our Caleffi Excellence. A single temperature for space heating and indirect water heater. So here's the system that's delivering 2 water temperatures. One's modulating, one's at a set point. If I go to multiple water temperatures, I get beyond 2, typically I have to add in some sort of mixing devices. Here I have a couple of manifold stations with mixing valves built in. The mixing valves are indicated by the blue arrows, delivering 2 separate water temperatures to different parts of the building. This is our win from last year for the Caleffi Excellence. Tip Top Plumbing up in the Winnipeg area. I think they're somewhere outside of there. But you look at this, and there's a whole lot going on. You know, on that back wall there, I can clearly see 3 mixing valves. And if you peer behind the piping, I think I see another 2 as well. An indirect water heater, some higher temperatures. You know, some of these systems residentially, when I get to the larger buildings, you know, the 15,000, 20,000, 25,000 square foot houses, a lot of times your systems become quite complex because of the different floor coverings, the different heat loss through the walls, and the different methods of radiation and the heating throughout that building. Now, before we talk about multiple temperatures, I need to talk about one temperature. Because what happens is when I do primary, secondary, there may be mixing going on that sometimes has contractors scratching their heads. Because from my past experience, I was involved a lot in other companies where I worked with people to design systems and then talk about the setup of them. And often there were instances where the end setting wasn't anywhere near the anticipated setting. And it's all about mixing in my hydraulic separator. Or if I'm doing closely spaced tees, closely spaced tees. You know, so here, this is actually an illustration out of one of Lochinvar's installation manuals. I have to say they have some great manuals. I've pulled quite a few pictures out for this presentation and others in the past. But if I look at that primary, secondary, inside the hydraulic separator, I really have 3 different flow combinations that can happen. What I really want to talk about is this one over to the right-hand side. The boiler flow less than the system flow. Now, what happens here is because of the boiler flow being less than the system flow, as you see in that diagram, return water will come up from the bottom of the return side of the hydraulic separator and mix with the boiler water coming out. And in this mixing process, it lowers the water temperature coming out to the system. Okay. Now, when this happens, it always becomes a question of, can I heat the building with this water temperature or can't I? Or even what temperature am I ending up with? Okay. So if I look at this situation, let's say for the aspect of our discussion, I'm flowing the boiler at 5.5 GPM, and the water temperature out of the boiler at that point is 160 degrees Fahrenheit. Now let's say the return water is coming back at 140 and the system's flowing at 10 GPM. The question always becomes, am I going to have the right temperature going out to the system to heat that system? Okay. This formula 1.3, it's all about calculating the mixed water temperature. It's directly out of the applicable hydronics. But if I apply that to my situation, what I'm going to find is the temperature going out to the system is leaving the hydraulic separator at 151 degrees Fahrenheit. So I've lost 9 degrees of temperature because of this mixing, because of the mismatch in flow rates between the boiler side and the system side. And the question always comes up from that point, is this going to be close enough in temperature to heat that building, or do I have to accommodate this change in temperature? Okay, couple of ways of doing it. Okay, I'm going to go to option number 1, and you'll notice it does say if available. Yeah, there are some boilers out there that will offer the option of doing what's called a supply sensor or a common supply sensor. If you look at the Lochinvar diagram off to the right-hand side, you'll see it up here listed as a system sensor. And if you notice looking at the plug here on the front of the hydro separator, it doesn't have that shiny brass look because somebody has converted it over with the well to put the supply sensor in there. What happens with this sensor is by putting that sensor in and feeding it back to the boiler, that now can become the control point. So if I need 160 degrees going up to the system, this common supply sensor ensures that the 160-degree temperature goes out to the building and the heating is satisfied with that water temperature. It may drive the boiler up to 170, 175, but the end result is comfort will be achieved in that building. Now, if the boiler doesn't have the option of doing that sensor, then it becomes a matter of figuring out how hot I need to run the boiler in order to give me the proper mix temperature after my hydraulic separation. So if I work the numbers backwards, now let's say I'm looking for 160 going out to the system, I want to be returning at 140, and the system is still flowing at 10 GPM and the boiler is still flowing at 5.5 GPM, then I can calculate what that temperature needs to be. So if I work the numbers through, I end up with 176 degrees Fahrenheit. So from a design standpoint, I need to run that system hotter, the boiler hotter, to drive the proper temperature out to the system. Okay. Now, the question is really about how many temperatures do you need to heat the building. I actually had a poll question that was supposed to happen earlier, but this seems like a great place to run it. So I'm going to turn it over to Bob and Woody to run our poll question.
Okay, we'll run it right now.
There we go. Take a minute, everybody, read that and click on it. We'll do an instant poll here and see kind of what you folks in the field are doing for your mixed temperature designs. There's a result. 7% said 1, 48% 2, heat and domestic hot water. That makes sense. 26% for 3 temperatures, and 19% said I don't have a typical system. So that I would agree with that. Most people have 1 temperature with a domestic hot water demand at a higher temperature. So there kind of gives you an idea from the field. Thanks everybody for that.
So, from that poll, it's interesting to see the wide variety of what people are doing. And from my past experience, that's what I typically saw. Indirect water heaters for a lot of contractors are definitely always part of the design, which are driving that second temperature. And then it's for the application of whether I need to do mixing for 1 or 2 additional temperatures. Now, one of the questions that always comes up, and I've had to field this a couple of times in the past, is when somebody goes in and they look at a system and they come back and they will say, they look at something like this, a design where somebody's done a radiant design, and they say, well, I need 95-degree water, I need 98-degree water, I need 110-degree water, and I need 105-degree water for radiant. Now, additionally, I'm doing some air handlers, and the air handler manufacturers seems to have a lot of their charts sized at 160 degrees. And, oh yeah, on the second floor, I'm going to do panel radiators, and the panel radiators should be sized at 180 degrees. So I've had times in the past where somebody says, can you design me a system with 6 mixing valves to deliver all of those temperatures? And my question really becomes, do you really need that number of temperatures? When I started to work on this talk with Caleffi, this is probably one of the more interesting conversations that Bob and I had about our past and with temperatures like this. And something that we kind of agree on is this rule of thumb when looking at mixing valves in multiple temperatures. And from a design standpoint, if I have temperatures of within about 10 to 15 degrees Fahrenheit of each other, from a design standpoint, we can group them together and consider them to be running at the temperature of the highest of the temperature choices. Okay? So what will happen is I'll take those 4 bottom temperatures and I create them as a single water temperature at the high temperature. So this way here I can get the mixing devices down to a smaller number. Now, I also want to throw out some design considerations which somebody should take into account when you start to look at designing and you have a fairly large number of mixing devices going in to take care of loads. Now, the first consideration, and actually this whole consideration is based on what water temperature do devices really need if I am designing the system and I have the option of possibly resizing equipment. So when I do a fan coil unit, most times people will say, I'm doing a fan coil, I need maybe 160, it could be 180 degrees Fahrenheit as the number that everybody comes up with. But if I look at this chart here, this is showing me sizing based on 120, 140, and 180 degrees Fahrenheit. So from a design standpoint, a lot of times I can change the water temperature so that I can better match different parts of my load to that same water temperature to reduce the complexity of my piping system. The one thing to notice is as I drop the water temperature, the heat output does drop correspondingly, so that does have to be accounted for. Same thing happens with panel radiators. This is a chart out of an Hydronic, shows typical panel radiator ratings. And of course, these ratings are based on 180 degrees. In that same Hydronics, we also show a reduction chart. So if I want to reduce the water temperature, I can reduce the water temperature, but I have to calculate a correction factor of what's going to happen to the heat emissions. How do I correct for that lower water temperature? So let's say I didn't want to run at, with an average temperature of 180, I wanted to run at an average of 140. So I use the chart above, that 140 degree water temperature with a 70 degree air temperature, which gives me a delta T of 70. I go in there, that 70 degree delta T gives me a correction factor of about 0.55. So I can derate the panels to this lower water temperature. Okay? I can do the same thing with baseboard. And most people think of baseboard radiation, the number immediately comes to mind is 600 BTUs per linear foot. Now that's where baseboard is rated. The reality is baseboard, as you see on this chart here, baseboard output changes with water temperature. So I can drop my water temperature, size my baseboard appropriately, and get to that lower water temperature. So I don't need 180. I can size baseboard down at 140. The thing to consider is that 180 for an application, I may need 4 feet of baseboard. When I drop the temperature down to 140, the amount of baseboard increases to 7 feet. So from a design standpoint, when I start to look at multiple water temperatures, particularly when I look at higher temperature applications, a lot of times I can resize the equipment based on a common water temperature and potentially reduce the overall complexity of my system to something a little bit more reasonable. And kind of following up on the Coffee with Caleffi I did last year on condensing boiler performance, if I can resize it and drop the water temperature, overall I'm going to improve my system efficiency. So if I come back to my rule of thumb and how many water temperatures I need, for that system that I was talking about earlier, I really need 2 water temperatures. I need 105 degrees Fahrenheit to take care of the radiant, and I'm going to go with 140 to take care of everything else, and that's after resizing the panel radiators and the air handlers to run off of 140 degrees. So from a design standpoint, I'm going to run the boiler based on that 140 degrees max water temperature, and then I'm going to mix down to 105 to take care of the radiant. Now the discussion is, how do I get down to that 105 degree number? Okay. So from a mixing standpoint, we're going to look at 4 different ways of getting there. We're going to talk about, I've heard it referred to as proportioning and proportional valves. I hear both of them intermixed. So we're going to talk about doing a proportional or a proportioning mixing valve. We'll talk about a thermostatic mixing valve. We'll talk about motorized mixing valves. We'll also talk about injection pumping. And as we talk about it, we'll talk about how to apply it, the pluses and minuses of using each style of multiple water temperature mixing. Okay? So I'm actually going to jump down to the second one on the list. We're going to talk about thermostatic mixing valves first. So thermostatic mixing valves, you can see the cutaway off to the left-hand side, and in the center there you'll see what's in bold listed as the thermostatic motor. So off to the right-hand side, I have that mixing valve in place. So it's going to have hot water coming in. Hot water is being delivered by temperature 1. The cold water is actually the cooler, I'm going to call it actually the cooler water, is the return water from my heat load. And the two of them are going to mix in the mixing valve to deliver temperature number 2. Okay. How it works, the thermostatic motor is sitting in the fluid flow. It measures the temperature, and it will move the cartridge to change the flow rate of the hot and cold water to deliver the set temperature, and the set temperature is set by the knob on top. Okay. Now, what are we really looking at here? Well, we're looking at a set point installation. So thermostatic mixing valves do not do outdoor reset. I set the temperature, it delivers a set water temperature. The big benefit of this is it's a good low-cost option. Okay? I'm just paying for a thermostatic mixing valve. It's not a mixing valve, a motor, and a control. Okay? It's also easy to set up. There's no programming. It's all about setting the temperature on the knob on the top of the mixing valve, the dial in the mixing valve, and then adjusting it to where you need to be for temperature number 2. So it's simple to control, and it's simple to set up. For me, this is really the best choice if I'm doing smaller radiant areas. So, you know, if somebody says I'm doing something, let's call it 200 square feet, I'm probably going to do a thermostatic radiant mixing valve. If somebody says they're doing a below-grade basement, I would probably also go with the thermostatic mixing valve. You know, below-grade basement, I probably don't need a whole lot of outdoor reset control. Okay? But for me, it's really about those kind of applications. Another great choice on the thermostatic mixing valves to simplify the system is a thermostatic manifold mixing station. It's all about simplifying the installation. So what I have here in the drawing, it shows 2 of those mixing stations where I have my pointer here, and here are the thermostatic mixing valves. But it's a manifold that does balancing. It's a circulator. It can be a smart circulator. And it's my thermostatic mixing valve in a single package. So from an installation standpoint, I'm just bringing supply and return up into here, and then all of that other work is done, making the installation simpler and quicker with this thermostatic manifold mixing station. Now, here's another drawing. Again, shoots a picture from our Caleffi Excellence program. Yeah. This is an installation that has some radiant. You can see the tubing off to the left-hand side, and it also has some high temperature. So circled in green is my thermostatic mixing valve, and that thermostatic mixing valve is providing hot water to the radiant at a lower water temperature than the water that's going out to the high temperature side of the system. The next of my option is a motorized mixing valve. So there's no thermostatic element. It's a mixing valve whose position is going to be driven by an electric motor. So one of the things that you have here is, in order to make this work, not only do I need the mixing valve with the motor, but I also need a control to determine where the mixing valve has to be positioned and to actually position that mixing valve. From an application standpoint, it's typed in very similar to the thermostatic. There's a hot port, there's a cold port, and there's a supply port. So hot water will come into one side. Typically, cold water comes into the bottom of most of your motorized mixing valves. And here's the outlet temperature that I'm driving as my lower temperature number 2. Okay? Now, to complete this package, in most cases, I'm going to do outdoor reset with it. So it requires an outdoor reset control, which requires an outdoor sensor. And I don't show it on the picture, but somewhere out on the piping of temperature number 2, there also has to be a sensor strapped to the piping to sense the outlet temperature so that the valve can modulate to drive to a specific set point. Okay? So it does require outdoor reset to work. Okay? The nice thing about this style, though, is it allows me to do outdoor reset, and it allows me independence from the reset that the boiler is running on. So I can pick a total independent curve. A lot of times I can go in there and I can set a maximum water temperature with some of these controls. I can do a different room temperature set point in the control itself and make a lot of adjustments strictly to this part of the building that doesn't affect temperature 1 or the high temperature side of the building at all. Okay? The other nice thing that I like about doing a motorized mixing valve is a lot of times I can integrate room feedback into the control. So after I go in there, set the parameters to where I think I need to be, what the room feedback will do is if I set a room temperature, and then based on the difference between actual and set point of room temperature, a lot of the controls can make adjustments on the water temperature to dial the room temperature directly to where it needs to be. And in most cases, it will drive the water temperatures down lower, which will help drive boiler efficiency. Now, the downside. It's valve, it's motor, it's control. It's installation work, it's setup. So the installed cost of a motorized mixing valve is always going to be considerably higher than doing a thermostatic mixing valve. Okay. Typically, when I look at motorized mixing valves, I'm probably going to start thinking about it if the area I'm trying to control, let's say it's more than about 1,000 square feet. Then I can start working and start thinking about the budget and probably justify the higher upfront cost of the thermostatic mixing, the motorized mixing valve. Here's a picture showing a motorized mixing valve. You actually have 2 boilers off to one side. Here's the motorized mixing valve here. Hot water comes in here from the boiler. Here's cold water coming back from the supply. And then it's moving up here through the pump. Something else I also want to point out, this box right up here, that is your sensor. So that's physically a sensor that's clamped onto the pipe, and that's measuring the water temperature out of the motorized mixing valve, which actually in this case feeds back to the boiler's control. And the mixing valve is part of the boiler's control package, where it will make the adjustment in the mixing valve's position to drive to the right water temperature based on what's programmed in there for the setting of this lower water temperature. Now, the third way of generating multiple water temperatures is through injection. Now, I'm going to actually focus more on injection pumping. There are other ways of doing injection as well. Now, the injection style of mixing really came about primarily with the non-condensing boiler side of the business. Okay? Outdoor reset hit the market, and with a non-condensing boiler, I always have to be concerned with the return water temperature so that that boiler doesn't condense. If a non-condensing boiler condenses, I can seriously shorten the life cycle of the boiler. So with the injection pumping, think of it as essentially 2 water temperatures, and then the injection risers making the connection between the 2. Okay? The loop over here with the boiler is the boiler loop. The boiler loop is kept hot, and it's kept hot enough so this non-condensing boiler is always above the dew point from the combustion process. Okay? On the distribution side, based, and I'll point out this sensor here, based on this sensor here, is always driving to a water temperature driven by the injection controller. So it's that water temperature, then it works the injection system to maintain that water temperature, and in most cases, that water temperature is running off of outdoor reset. Now we're going to look at a close-up of that injection riser system. So it's two pipes, and the pipes actually can be a lot smaller than the rest of the piping in the system. And what it's used is to bring hot water across from the boiler loop while at the same time bringing colder water back to the boiler loop. Now, the hot water coming from the boiler mixes with that circulating water in the distribution system, elevating the distribution system water temperature to where it's desired through the control. Now, when the cold water comes back in the return riser, it mixes with the hotter boiler water, elevating that return water up to a temperature that condensing is not an issue with that boiler. Now here it shows a variable speed injection pump, and there's also a metered balancing valve on the opposite leg. Now I have to make sure that that injection pump is running with enough essentially head loss between the two legs so that I can control it. So probably one of the most important things to do on here is have a metering valve and set the metering valve so that mixing pump, that injection pump, is in the location where it can actually meter and monitor and inject at the proper rate. So here's an example of a distribution loop for an injection system. And on the top where I have the words injection riser, here's the risers coming into that loop. So one of the nice things about doing this injection system is a lot of times it's just the injection risers that are being distributed through the building to injection distribution loops like you see here. Now, the fourth way that we're going to discuss is what's called the proportioning valve. Okay, everything so far, the control has had everything has had a certain level of intelligence in the control. Thermostatic mixing valve has its thermostatic element that will maintain a set point temperature. The motorized mixing valve has a control that senses temperature downstream, and in most cases from doing outdoor reset, senses outside temperature and modulates the valve to drive a water temperature. The same thing happens with injection pumping. Now, with a proportioning or a proportional valve, there is no motorized unit. So if I look at this picture here where I have it circled in green, light green there's a manually set three-way valve. Looks fairly similar to this. One thing I will point out, the figure that I brought up, the ports are not in alignment with my drawing. So if you try and equate one to the other, it's really about equating the hot, the cool, and the mix as far as where the ports are versus where they actually show up on that drawing. And then from the aspect of setting, there's just a knob on there, a dial, that I will change the position to change the mix rate within the valve itself. How does it work? Well, if I can take this valve and take a setting, I'm going to have a proportional mix of how much hot water goes into the valve and how much of the cooler return water comes in. Let's say let's call it a 70-30 split. It could be 60-40, it could be 50-50. Now, I'm just making up this number as I go along. But what happens is once I set that valve in position, that split between the hot and the return water is set. It's always going to be at the same proportion. Now, what that does for me is because it's now proportionally mixing, now let's take a look at the chart 4-9 that's off to the side. If I have something upstream of this proportioning valve, it could be the boiler, it could be a motorized mixing valve, and if it's changing the water temperature based on outdoor reset, since this proportioning valve is proportionally mixing that water, I now have established a secondary outdoor reset curve. So when the inlet water to the valve, the heat source water, is running at a higher temperature, the proportioning valve puts out a higher temperature. As the water temperature drops on the heat source to the proportioning valve, the outlet temperature drops proportionally with it. So it gives me that extra outdoor reset control. Now, the nice thing about this is if I implement a proportion valve into the system, I get outdoor reset at a much lower price than what I would have gotten if I had gone with the motorized unit and gone with the control package to operate the motorized mixing valve. So no extra control is needed from this point. Now the downside is, from a operational standpoint, there is nothing that there's no logic that can make adjustments if something changed. So this is, this has to follow along with somebody else's outdoor reset control, and I don't have the ability to tailor it specifically for a portion of the building that I would if I had an independent valve that has some logic and some sense built into it. Design-wise, I normally will see it installed in something like this. So here's a radiant load over here with the manifold. Here's my pump. Hot water is coming in. Is my return water. And in that proportioning or proportional valve, there's a setting that a mixing occurs based on the handle setting that gives me a lower water temperature that's what's coming in. And again, as the incoming water temperature drops, the outgoing water temperature drops proportionally with it. So when I look at delivering multiple water temperatures, it becomes, let's drive a water temperature out of the boiler, and then let's apply, it could be a thermostatic mixing valve, it could be a motorized mixing valve, it could be a proportioning valve, or it could be injection pumping to give me that second, third, or fourth water temperature, depending on what we need. Now, one of the things that we're always interested in is how do you do things? So again, I'm going to hand it over to the boys to run a quick poll on what method of delivering a lower water temperature do you utilize?
Okay, we will launch it right now.
All right, just basically asking you guys what you typically use to do your mix down temperatures, the different methods that Jody's gone over there, and we'll see what's going on out there. One thing, if I could throw in there, Jody, is when using the thermostatic mixing valves, just be aware of the CV of the valve. If you buy an off-the-shelf thermostatic mixing valve and try and use another radiant application, just be aware of they're typically a fairly low CV valve. Now, the ones that Caleffi offers are built specifically for radiant mixing, much higher CV, and that's why you see those in our manifold mixing stations and other places. It's a higher flow valve than your typical off-the-shelf thermostatic valve.
Excellent point, Bob. One other thing on that I actually didn't cover, but the other thing when you're doing mixing valves, check with the manufacturer, because whether I'm doing a motorized mixing valve or a thermostatic mixing valve, there's a minimum temperature drop that has to occur over that valve. It could be 14, it could be 18, it might be 27 degrees Fahrenheit. But there is going to have to be a certain temperature drop that allows that mixing valve to operate properly.
That's right, thanks.
There's your answers.
Yep, there's our answer. So thermostatic mixing valve, 36%. Motorized second at 17%. Proportional way down, 2%. Yeah, it's a dumb valve. It doesn't do a lot for you. Injection mixing, like you said, that was popular back when we had non-condensing boilers at 12%, and then depends on the application to 33%. So thermostatic mixing, 36%. Depends on the application at 33%, and the other one's in between there. So again, thanks everybody for the information and participating. Take it away, Jody.
Oh, thank you. And I'm pretty much with you guys at that 33%, because for me, it really becomes a matter of how do I best attack the problem, the challenge, and it really never comes down to what's the best solution. It's really what's the best solution based on the homeowner's requirements versus the budgeting for the installation. One other thought on that I am going to throw out there is having done a lot of outdoor reset, the one thing that always will tend to drive me to making the selection for thermostatic mixing valves is when somebody comes in and they talk to me and they say, you know what, I'm doing a project and I think I want to do radiant in all the bathrooms. And my question always to them is, are you looking to do radiant heating or are you looking to do floor warming? Because the reality is, you know, if depending on the design of my radiant system, you don't get a whole lot of floor warming when you're putting out 80 or 82 degree water out to that floor. And I've had guys that say, you know what I'm doing, I want to do radiant heating, and then they come back, you know, maybe a month later, and their question is, Jody, how do I lock the water temperature in at 90 degrees or whatever number they happen to have? You know, so we start to look at it, you know, if guys that know me know that I'm a big fan of outdoor reset control, but the reality is it has to be a mix of technology, because when the day is done, it is about driving comfort in the eyes of the homeowner. Okay. So we talked a bit about driving the temperature down. How do I drive my highest water temperature, and then how do I mix that water temperature down to where it needs to be to provide the right water temperature throughout the building to take care of all the individual loads? The flip side becomes, how do I boost the water temperature to take care of domestic hot water? You know, because when I start to look at doing outdoor reset, I tend to, you know, and I'm doing outdoor reset and I'm driving my water temperatures based on thinking about particularly maximizing the performance of a condensing boiler. In most instances, I'm well below the temperature that I want to be to recover an indirect water heater. You know, outdoor reset, the temperature changes over the heating season. When I do an indirect water heater, it's all about set point. What water temperature do I need to maximize the performance of the water heater, or meet the needs of the building for that water heater? Now, the first question comes up when somebody says they're doing an indirect. My first question always back to them is, are you going to do priority or not? In a priority system, domestic hot water receives priority over a space heating load. So if I look at this drawing, again, another nice drawing out of the Lochinvar installation manual. So here's my boiler. Here's my indirect with its own circulator. I have a boiler circulator here. I have a system circulator here. If I have it set up for priority, and I'm not really sure which one the Lochinvar kicks off, but in priority, at least the boiler circulator and possibly the boiler circulator and the system circulator shuts down, allowing the indirect water heater to receive the full output of the boiler to quickly recover the volume of water in that water heater. Now, usually when I start to talk about this, I'll have guys that immediately will say, well, I want to do non-priority. I can't cut the heat off to the house. The homeowner is going to start to complain. And I'm from New England, or New York, or Pennsylvania, or New Jersey, somewhere in the Northeast where the guys probably grew up in a house that had an oil boiler, and that oil boiler had a tankless coil in the boiler. For those of you that are in other areas where the tankless coil boiler was not utilized a lot, the tankless coil was utilized to provide hot water in the same package of the boiler. It's the coil that sat in the water of the boiler, and I simply passed the domestic water through, and it used the mass of the boiler and the firing rate of the boiler to heat the water. Now, to make sure that it would produce enough hot water, it ran off of what's called a triple acting aquistat. You can see it over here on the front of this happens to be a peerless boiler. You can see a port for it right here. Now, what the triple acting aquistat did is the third feature that gave it the triple name was a low limit. So if the water temperature in the boiler hit a low point, it would shut down the system circulator. That way there, the full output of the boiler could go to generating hot water. And I think if you talk to anybody in the Northeast, somewhere in their life, they live with a boiler with a tankless coil. This, in fact, was what was in my basement growing up in southern Maine. Now, with this, somebody lost heat as they used hot water once the boiler temperature came up, and it would release the circulator and would start back up again. You talk to anybody that grew up in the Northeast, and they probably didn't even know that they lost hot water. In most cases, it's not apparent. So when I start to look at priority and somebody says, should I do it? A lot of times, we go through the full discussion of this. The other discussion I have with them is, what is the homeowner's expectation? The thing that I always cringed at whenever I was in the field with a contractor is when they utter the famous words, you'll never run out of hot water. So if I look at these charts, these happen to be Squire charts. When I look at a water heater, it's rated at a certain temperature, 180 degrees, and I'm looking at the 30-gallon tank. It has a flow rate of 8 GPM, and with a 60,000 BTU boiler, if you look at the lines there, I can produce 136 gallons of hot water first hour. That's pretty impressive for a 30-gallon water heater. But the reality is, if I have a 60,000 BTU boiler installed in that house and I'm running non-priority, that water heater is not going to get that 60,000 BTUs. Depending on the load of the building, it may be 50, it may be 30, it could be 10. So without priority, it always, for me, always becomes a question of where I am going to end up from a performance side of things. Now, the other thing that I tend to see driving priority is where you're hooking up the indirect water heater. This happens to be a drawing out of our wiring diagrams for our controls. So a lot of boilers require the indirect water heater. We'll show drawings that you see here off the boiler prior to your hydraulic separator. From this aspect, I like it from the idea of it's there during the non-heating seasons. I've minimized the amount of the piping system that I have to heat up, and I'm only running a single pump to recover the indirect water heater, rather than running a pump to bring the hot water out to the hydraulic separator, and then the pump to bring the water from the hydraulic separator into the indirect water heater. The problem doing this application with particularly a high loss heat exchanger is, if I size this circulator here, here's my mouse. If I size the circulator here for that 8 GPM, I bring the system circulator on because of the increased head loss, now trying to parallel two circulators through the boiler. The flow rate through both the hydraulic separator and the indirect water heater drop off. So with this one here, I always pull for, if I'm doing it prior to the hydraulic separator, let's do priority. Now, this blow up down here, if I do this through one of our controls, the control does have a pair of end switches. Because the reality is, I have to indicate to the boiler whether I'm doing space heating, which means I'm running off of outdoor reset, or I'm doing priority, my set point, which is requiring a set point number. So here I have XX for doing, to bring that back to the boiler. The boiler runs off of its control, giving it outdoor reset. And then most of the boilers will have a secondary contact for priority. Here it's listed as DHW/VCCR. I connect there back to the priority contacts, and then the boiler goes to firing a set water temperature to recover the water heater. Now, if I don't want priority, or I'm looking at a water heater that sometimes we end up here based on the boiler has a high head loss, The Indirect has a high head loss, and this will get me into a much smaller circulator. Or I want to run non-priority, I can put the Indirect after the hydraulic separator. Now, once I bring it in after the hydraulic separator, then I can run non-priority and not have to worry about the two pumps in parallel pumping through the boiler. Now, the other thing with this, particularly if I'm running non-priority, as we talked about earlier, I do have to accommodate and account for the temperature drop. Because all of a sudden, if the heating system is running non-priority, and I'm flowing that part of the system at 10 GPM, I bring the indirect water heater in, that adds in another 18 GPM. What I'll actually see is the outlet temperature for my hydraulic separator drop. So that has to be considered when I'm going non-priority and I am putting the indirect water heater after the hydraulic separator. Now, I want to talk a little bit about doing domestic hot water with an indirect water heater in a commercial building. Commercial buildings, I can't remember the last one I saw that was running priority. It's all going to run off of non-priority. Now, the challenge becomes, in a lot of these applications, I run into a health club, a hotel, a motel. There's a wide variety of applications out there where we're putting in an indirect water heater, and the demand for that indirect isn't just about little blocks of time of 10 or 15 minutes. It may be that the call for hot water lasts for an hour, 2 hours, or it may be that the hot water is demand that occurs for 6 hours a day. So what happens is I put my boiler in, or boilers in. It's probably going to be a multiple boiler application. Just as with a residential application, I'd like to run the system, building off of outdoor reset control, and I want to run set point for the indirect water heater. So the indirect calls, the boiler control says, okay, I have a call for indirect. It provides 180-degree supply water out to the entire system. And let's say I have a 30-degree drop across that coil in the indirect. Coming back at 150 degrees. Okay. Now, additionally, the rest of the system is going out at 180, and it's also coming back somewhere probably in that 150 to 160 degree range. The boiler runs now, the boiler's efficiency reflects this as the return water temperature. Now, for the sake of our argument, let's say that when I recover the indirect water heater, the indirect is requiring 80 GPM. Let's say to heat the building is running at 130 GPM. I need numbers to work with as I work through some calculations. Now, although the building receives a single water temperature, and this is something that I actually picked up from the guys over at Wiesman, let's put the building on a motorized mixing valve. Let's put the building on this mixing valve so that when the system runs for long periods of time where the boiler has to run hot to recover the indirect water heater, the mixing valve can drop the building's distributed water down to a much lower water temperature. So the water coming out of the boiler may be coming out at 180, but what's being supplied through outdoor reset, let's say it's leaving the mixing valve at 130 degrees Fahrenheit. Passes through all the heat emitters. Let's say we're doing a 20-degree drop. It comes back at 110. So all of a sudden, the return water temperature is not 150. It's lower because it's mixing with this 110. If I do my numbers using my mix temperature formula, boiler is coming back at 125 degrees. So all of a sudden, by adding this mixing valve into the package, I now have a water temperature that can get this condensing boiler to condense, and it runs more efficiently. The question always comes up, how much more efficient can it be? Last week talking with Steve David over at Wiesman, they do run a program. It's called CPEP. It stands for Commercial Project Evaluation Program. And he tells me that adding in this motorized mixing valve into commercial applications, normally the mixing valve will pay for itself between probably 1 to 2 years, depending on the size of the building. So when you start to look at this in driving efficiency, this is something that can really help in these large commercial buildings that you're doing domestic hot water and you do have that large hot water demand. So it's a way of pushing the efficiency through the system. Now, the other thing I want to also note about this is when I do a multiple water temperature system where some of the water is going out at a higher temperature and coming back at a lower temperature, this also applies to my multiple water temperature systems as well. So if I have a high temperature going out at 160, coming back at 140, and I have a low temperature system going out at 105, coming back at 95, it is going to give me a blended water temperature that will give me a much better efficiency than just the higher water temperatures. So, kind of summarize it up. Yeah. From a design standpoint, it's all about driving the right temperature from each emitter. It's about driving comfort and it's driving efficiency. You know? And when I start to look at it from a design standpoint, I like to keep it simple. Let's combine temperatures where appropriately, and when I have items that may require different water temperatures, are there options to change the sizing of the equipment so I can run more heat emitters off of the that's a single water temperature. Yeah. The other thing is our last discussion we had there. You know, if I have a higher temperature as needed, a Pyrrhic load for a Pyrrhic load like domestic hot water, it's really about planning for integration. Where do I tie it in? Do I prioritize? Do I not do priority? How do I get the boiler to fire up? So there's usually some thought into the whole process of adding domestic hot water to maximize the system's performance. And finally, when I look at a multiple water temperature system, if I can start looking at some of these, integrating some lower water temperatures into the return to the boiler, it can help from the efficiency standpoint by dropping the return water temperature and pushing the efficiency of this condensing boiler up. Now, with that, I'm going to turn it back over to Bob Brewer.
Well, gosh, thanks. That was a lot of information there to digest. You did a good job getting it in there. One thing, if I could add, is a lot of the new boilers have multiple mixing potential right in the control on board the boiler, so that does take some of the cost out of it. And I think some of them now actually have multiple outdoor reset curves available too. So look into that when you're shopping your boiler. You might have the equipment you need to do these multiple temperatures already on board the control there. So we had a couple questions there. I don't know, Mark, do you want to do some questions, or let me go through the last couple housekeeping slides here?
I have a couple of questions, Bob. One is, let me pull it up here. Okay, Viessmann boilers run a Viessmann boiler runs continuously as opposed to other boilers that ignite after a TT demand. Do you care? Does it affect efficiency or operation? And do you prefer one boiler strategy over another?
No, that's a loaded question. My preferred strategy really doesn't come back to really whether the boiler is running continuously off of a TT contact. I prefer to run, it's about outdoor reset and finding the lowest outdoor reset curve possible. So if I am using an end switch to bring the boiler on, my goal is to keep that end switch closed 60 minutes out of every hour. Let's select the heating curve that drops the water temperature down to keep the heating system in balance with the heat load of the building so that the call is always there, because the end result is if my thermostats are ever satisfied, that means that I'm putting a little bit more heat into the building than it actually needs, which means I could probably drop my water temperature a little bit lower. So I like it. I like it both ways. I like the idea of having control with the TT contact, but in reality, my goal always is to drive the water temperature down as low as possible which tries to push me to outdoor reset. It's out to continuous circulation, which means there's going to be a constant call on the system as it stands.
Okay, very good. Another question is, if I'm not doing outdoor reset and I have non-condensing boilers, what are some key strategies in maximizing that boiler's efficiency?
Really, from a water temperature, if I'm not, well, the first thing that you should look at is what I would start with is what's the lowest water temperature I could run that boiler and still maintain temperature in the building. For instance, when I moved into my house had an atmospheric gas-fired cast iron boiler. The aquistat on the boiler was set that whenever a thermostat called, the boiler went up to 200 degrees. Now, one of the things that I did before I switched over to a condensing boiler is I wanted to know where my balance point was for water temperature and adequately heating my house. I took the aquistat and cranked it all the way down to 160. By dropping it down to 160, my water temperatures dropped, and amazingly, my house continued to continue to heat. Now, a little rule of thumb out there, I actually learned this from Richard Trethewey. It's called the 3 to 1 ratio. For every 3 degrees I drop my water temperature, my system will run 1% more efficiently. So really the key is, as I drop the water temperature, the system runs more efficiently. So if I can go into a building and, let's say, drop the water temperature 30 degrees, my system should be 10% more efficient. Yeah, so that, for me, that pretty much is, in a non-outdoor reset situation, that's really what you can do to drop your efficiency. And of course, the flip side of things, somebody says, how do I be more efficient? One of my first responses is always improve your building envelope. So if I can drop the amount of heat that's coming out of my building, then I don't have to put as much heat into it, and I can be more efficient from that standpoint as well.
I think that's it. Well, thanks, everybody. I know we ran a little bit late, but thanks for hanging in there. We'll see you in a month. If we don't see you down at the ASHRAE next week, thanks, everybody, and have a good day.